The power of frameworks is that they are easy to use. The problem is that they can create a layer of mystique to the fundamental logic of neural nets, a daunting issue for newcomers. Don't get me wrong, neural nets come in tons of flavors and can be incredibly complicated, but at the same time, the fundamental logic of a neural net only consists of a few pieces. In order to demonstrate the power but also unveil the logic behind neural nets, we're going to build an extendable framework piece by piece. Of course, the modern production-ready frameworks have far more bells and whistles, but hopefully seeing how a basic neural net framework can be built will help give newcomers to the field more confidence when they use those tools. But before we start talking about neural nets, let's talk about mushrooms. When our neural net is complete, we'll need a way to measure our success. To do this, we'll use the mushroom dataset from UCI. For those of you not familiar with the mushroom dataset, it is a set of 8,124 samples with 22 distinct attributes. Our goal is to determine if a mushroom is poisonous or edible based on those attributes alone. The distribution is around 50-50, and our goal for the neural net to learn the patterns in the data, at the very least, beat randomly guessing. I said earlier that the data was randomly distributed. It is a good habit to create a baseline measurement before you analyze a given machine learning technique. This will help you be objective in determining if your model was a success, as well as giving you an idea of what to look for early in training. For this training, we'll use a random guessing baseline, but if your goal was to compare the effectiveness of one technique to another, you could easily select another method like naive Bayes or KNN. A neural net in its most simple form is a series of nodes which connect to each other with some threshold to distinguish a decision. This process is meant to mimic the inner workings of our brain's neurons. The theory goes that by combining a lot of these nodes together, we can create a network capable of processing data and improving itself based on its output. The network would learn to detect certain patterns in the data based on repeated exposure to information and improve with time. Neural nets come in many shapes and forms, which is why frameworks are so important when working with them. Now let's start learning about those building blocks. The first piece to know is called an activation function. An activation function is quite simple. It is a mathematical function that transforms the output of a node into the input of the next. One of the reasons to use an activation function rather than feeding nodes into each other directly is that activation functions can prevent numbers from exploding into one direction or the other. Another advantage is that activation functions allow neural nets to learn complex data that linear models would otherwise be incapable of learning. They allow the model to bend the data of sorts to learn complex shaped decision boundaries. The math behind a neural net is pretty simple. There are two directions, the forward and backward direction, terminology we use for all of our components. The forward direction takes the input and passes it into the activation function, and the backward pass uses the derivative of the function on the data from the output node instead, hence the naming forward and backward. It is important to pick functions that are differentiable for this reason. The Rayleigh activation function, or rectified linear unit, is an extremely popular activation function, perhaps the most popular. The main advantage of the Rayleigh function is that it is incredibly mathematically simple while still being nonlinear. This allows the neural net computation to be very fast, because activation functions can be called millions of times, and so speed does matter. Furthermore, the function has been proven to be able to approximate complex nonlinear functions when aggregated despite its simplicity. The final advantage of the function is that it does not suffer from the vanishing gradient problem that plagues many activation functions. The Softmax function is the multidimensional generalization of the sigmoid function, which is used in binary classification. The biggest advantage of the Softmax function is that it produces very nice looking outputs. This is because they look like probabilities. The total of the outputs sums to 1, with each being a fraction of that value. Another advantage is that the function combines nicely with the cross-entropy loss function, a very popular loss function. Since the most common application of the softmax is the final output layer, the gradient of the softmax has to be combined with the gradient of the cross-entropy loss function in the prototypical use case. Luckily for us, these two gradients combine very nicely and simplify our life, so we don't need to get into the nitty-gritty of the two gradients. The next component we must look at is the layer class. A neural net typically is composed of a series of layers which each have defined dimensions. Similar to matrix multiplication, the outbound dimension of the preceding layer must match the inbound dimension of the next. There are different ways to visualize and count layers, but essentially a layer has an input size, which can be a number of features in the data, and an outbound size, which is the desired number of output classes. If we want to make our network more complex, we can start adding new layers in between as long as we preserve the first input size and the last output size. These layers created in between are called hidden layers, since the observer has no notion of their existence. Making good decisions in regards to how many hidden layers and how many nodes each layer should have is an important part of building and designing neural nets, as it determines what kind of distributions of data can be learned, as well as how much information the network can store. There are many kinds of layers that serve different goals. For instance, we have convolutional layers, which are frequently used in image processing and rely on kernels. For our use case, however, we can focus on fully connected linear layers. The math for linear layers is very simple. Every linear layer has a matrix of weights which corresponds to the input and output dimensions of the layers, and a bias vector, though some refer to this as W0. First, we randomly initialize the weights. The reason for this is to allow each node to learn different information about the data. By subtly shifting each node's weights, we can potentially prime them to learn different things. Next, during the forward pass, we simply use the normal slope and y-intercept equation to calculate the layer output, but with linear algebra. This output is what goes into the activation function before going into the next layer. Then, in the backward pass, we simply need to update our weight vector using the gradient, which is calculated by the neural net during the network's backward pass. The layer itself does not need to handle the gradient calculation. This step, where we shift the weight matrix in the opposite direction of the gradient, is the optimization step. We will discuss what an optimizer is and how they work later. The next component is the loss function. We touched briefly on loss functions when I mentioned the combination of softmax with cross-entropy loss, but at the high level, the loss functions give us a way of determining how far we are from an optimal output. This allows us to measure our network's performance as well as attempt to shift the network in directions that might improve the results. Like we said earlier, the cross-entropy loss function pairs nicely with the softmax and expects inputs that the softmax function provides. The other benefit is that the loss function is a relatively simple calculation for both the forward and backward pass. Notice how simple the gradient calculation of the combined softmax and cross-entropy loss functions are. The final component before we can bring it all together is the optimizer. There are many optimization techniques, but the high-level goal of the optimizer is to determine how much to shift the weights of each layer based on the gradients. Some methods track data over multiple time steps and do calculations to give the optimizer momentum, but the simplest optimizer and most commonly known is stochastic gradient descent. In fact, its logic is so fundamental that it is the underpinning of many popular optimizers like Atom. The logic of SGD is very simple. Once we calculate the gradient of the weights with respect to the loss, all we need to do is shift the weights lightly in the opposite direction. In theory, this moves us in the opposite direction of the loss and should improve our neural net. It is crucial to pick a learning rate that isn't too high but also isn't too low. One of the biggest factors that can determine the success of optimization is if the neural net gets stuck in a local minima. If the learning rate is too low, the network will never escape the local minima, and therefore the network won't reach optimal performance. However, if the learning rate is too high, the optimizer may never converge, as it will keep jumping back and forth. This is where learning rate decay becomes important. Starting the learning rate at a higher value and weaning it off allows us to explore more of the space and helps with convergence. Now that we have all our components, the final step is piecing it all together. The first step is the forward pass. Luckily, the forward pass is really quite simple. All we do is take the input data and feed it into each component of the network. So first we would push the data through the first layer, then through the first activation function, then the next layer, etc. The result is simply the output of the last activation function. If we want to determine which class the network selected, all we need to do is find the index of the maximum result. The backward pass is where things get tricky. The logic of the backward pass is straightforward, but the implementation tends to be where people make mistakes because of the various moving pieces. The first step is to push the input data through the forward pass. This gives us our predicted scores. Since we also know the correct labels, we can calculate the loss using the loss function. The loss function allows us to calculate the gradient with respect to the loss. Remember that this is the value we need to provide to our optimizer. The issue is that the gradient is not the gradient for each layer. We need to use chain rule to unravel the gradient backwards through the network following the reverse order of the forward pass. This is why the activation functions have backward passes as well. Each time we calculate the gradient of a layer, we need to store this value for later. Once we have calculated the gradient for each layer, we can hand those values off to the optimizer, which will attempt to improve the network. That's really all there is to implementing a neural net. Now that our neural net is working, the question becomes, how do we train it properly to produce the best results, and what kind of issues should we be wary of? The first step is to prepare the data. We typically want to use 3 data sets, but a minimum of 2 is necessary for getting clear results. The first set is the training set, and this represents the majority of the data. This, as per its name, is the data that we will train the network on. The validation set is the set of data that we use periodically to measure the network's ability to work on data it was not trained on. We do not train the network on the validation set. We only use it to validate the results and inform our decisions. Finally, we have the testing set, which can be used at the very end of training, much like the validation set. The difference is that we are tuning our model's parameters and structures. We often use the results of the validation set to determine what to choose. This means that we have managed to overfit our data to the validation set despite not training on it. This testing set serves as a final unbiased judgment of our success. Some important terminology is that an epoch is a full unit of training. This means that we train the neural net on the full set of data each epoch. This can be the same data, it could be different random subset of the training set, or it could be the training set but with randomized order. We often train for many epochs, as many as thousands or more depending on the task. A batch is a chunk of the training data. For efficiency reasons, we typically do not want to run the backward pass on every single piece of data because of how computationally expensive it is. Instead, we create small batches of data that we train on all at once. Overfitting is when our network learns the training set well but fails to generalize to unseen data. Now that we know how to train our network, an important step is often to visualize these results. By keeping track of the accuracy and the loss throughout the training process, we can get a good indicator of when our network fails. This is when our baseline that we built at the very beginning can come into play. We can run our baseline values through the same loss function and calculate the accuracy over a series of epochs, which allows us to plot the two methods against each other. These graphs are the output of training our neural net on the mushroom dataset, exactly following the notebook steps. There is some randomness in the training, but our network consistently achieves near perfect accuracy on training, validation, and testing. Now, not all problems are well suited for neural nets, so they are far from a universal solution. But hopefully this has helped unveil the workings of neural nets and given you more confidence in using the many powerful frameworks out there.